Hello friends, welcome back to the online lecture series of fluid mechanics and continuing with our ongoing topic, which is the physical properties of fluids. We will discuss another property. So far we have discussed many other physical properties of fluids, namely mass density, weight density, specific gravity, then coefficient of compressibility, dynamic viscosity, as well as uh, kinematic viscosity. We have already discussed the Newton's law of viscosity, and on the basis of that we have classified fluids as Newtonian fluids and non-Newtonian fluids. Today we will see another interesting property, which is called surface tension. But before that, let me ask you some questions. That have you ever wondered why the water droplets are always spherical in shape? Or if you spill mercury on the floor or on a smooth surface, the mercury forms small droplets which you can even gather again by using a paper also. Also, we know that we require pumps if we want to raise water from the ground level to the top of our terrace, but the trees does not. They do without using any pump. They uh, uh, they raises the water from the underground to the topmost tip of the tree. Also, you might have seen that many insects can walk on water or even run on water as if the water is acting like a stretched membrane. Now, all these phenomena that is occurring is because of this surface tension, and we will discuss about that topic today. Now, there is one phenomena which differentiates between liquid and gas, which the liquid is capable of, but a gas does not. That is the formation of an interface. Now, what is an interface? When a liquid phase comes in contact with another liquid phase or gaseous phase or even a solid phase, then we find that a boundary is formed which separates the two distinctive phases. Now this boundary which is formed is what is referred to as an interface. So let us discuss about this interfacial phenomena. Here, as you can see here, we have tried to draw that the formation of an interface between a liquid phase and a gaseous phase, or between one liquid and another liquid, provided that both of them are immiscible liquids, or even between a liquid and the solid phase. An interface is always formed, and among fluids only liquids forms an interface. Now let us discuss about interfacial phenomena. Here we consider an interface that is formed between two fluids, one in liquid phase and the other is in the gaseous phase. For convenience, let us say that this is water and this is air. Now we know that uh, similar molecules are attracted towards each other and the force is called as cohesive forces, whereas the dissimilar molecules such as water and air, they are also attracted towards each other and the force of attraction is known as adhesive forces. Now, if we consider here the molecules which are located in the bulk of the liquid, here you can see that they will have identical interactions with all the neighboring molecules. So the molecules in the bulk, they will have identical interactions. Means the molecules are attracted towards each other like this, and this happens for each and every molecules in the bulk. So everywhere we can draw the mode of interaction between the molecules, and as can be seen, they are in a state of symmetry. They are attracted towards each other by cohesive forces. In fact, in case of organic fluids, these cohesive forces are because of the van der Waals forces, and for polar liquids like water, these may be because of the hydrogen bonds. Now, we know that the density of liquid is greater than that of gases, and so the compactness of the molecules in the two phases are also distinctive. The molecules in the interior of the fluid mass, that is the bulk, are attracted by the surrounding molecules, and these cohesive forces balances each other because of the symmetry which is which can be seen here. But the attractive forces, what are the how are the attractive forces for the molecules that are located at the interface? Let us draw that. See, again here we will have the cohesive forces between the water molecules, but it seems unsymmetrical, as above the interface we have another phase that is having another fluid, which is air. So here we are having air. Of course, the water molecules may be attracted by the air molecules also. So you can draw it by these dotted lines. However, this adhesive forces is very less or negligible as compared to the cohesive forces. So overall, what is happening at the interfacial molecules? The attractive forces acting on the interfacial molecules, these are non-symmetrical, and the attractive forces applied by the gas molecules above are usually very small, and therefore they are incapable of balancing the forces on the surface molecules. Now, as a consequence of which, there you can see that there is a net attractive pull acting on these interfacial molecules towards the interior of the fluid or towards the bulk of the fluid. As a result of this, the interfacial molecules may ultimately get dissolved in the liquid and get lost. But this does not actually happens, because an interface is always formed between a liquid and another liquid, or between a liquid or gas, and this is the very fact that the interface will always be formed. So what is the reason for this? To make this possible, the interfacial molecules must possess sufficient energy, which restricts the net inward pull to take these interfacial molecules towards the bulk of this liquid. And that sufficient energy which they possess is what is referred to as the surface energy or interfacial energy. This interfacial energy, in fact, it is proportional to the area of the interface that is formed. Hence, we can say that as a consequence of the unbalanced forces on them, the interfacial molecules are pulled towards, are pulled inwards, which they overcome on account of possessing this surface energy or interfacial energy. As a result of which, we can say that a hypothetical skin or membrane is considered to be acting in the plane of the surface and is stretched over the fluid mass. Now, rather than presenting a detailed molecular picture, we must represent a gross manifestation of the underlying interaction. Now, this is achieved by introducing a macroscopic physical property which is known as surface tension. So, now the surface tension, this may be defined as, in fact, the coefficient of surface tension, it is denoted by the letter sigma, and this is defined as the surface energy or the interfacial energy per unit area of the interface. Now we know that the unit for energy is joule, so the unit for the coefficient of surface tension will be joules per meter square or per square meters. So we have joule per meter square as the unit of surface tension. Now this surface tension can also be expressed in the form of a force, because we know that 1 joule, we can write joule as Newton meter. So for sigma we have joule per meter square. Now if we replace this joule by Newton meter, we can write Newton meter upon meter square. Now 1 meter gets cancels out and we get Newton per meter. So now we can define this coefficient of surface tension, or surface tension may be defined equivalently as the force per unit length that is acting along the line of the surface. Now it is due to this force that the intermolecular sorry It is due to this force that the interfacial molecules are always in a state of tension, and it appears as if the interface is acting as a stretched membrane. So for an interface which is formed, we can represent it like this. Suppose we have a container that is filled with some sort of fluid. So this is our interface. We can represent it like this, and the surface tension forces are acting. Now, because of this surface tension force, the interface is always in a state of tension, and it acts as a stretched membrane. In two dimension also, we can redraw this as the form of force. If we represent, we can draw it as a single line with the surface coefficient of surface tension that is acting, or the surface tension force that is acting. If we have curved interface, and we can represent the surface tension force like this. So this is again sigma. For mercury, we will get curve like this. So here also we can represent the surface tension like this. Now let us see how this surface tension helps to keep any system in equilibrium. Now first is the energy minimization principle. I've already given you some examples at the beginning of the lecture, such as water forming, that the raindrops are always spherical in shape, or water on a leaf beads up, or the small droplets of mercury will form into spheres when they are placed on a smooth surface, or even the formation of soap bubbles, or even you can see that a leaky faucet always trips. Now this is because of the energy minimization principle attributed because of the surface tension effect. Now what happens here is that a liquid which is placed over a solid surface, it tends to minimize its net surface energy in an effort to come to an equilibrium state. We know that sigma is equal to, we have sigma is equal to surface energy upon area. So in order to, so we can rewrite the surface energy as sigma into area. Now our purpose is to keep the surface energy to be minimum. Now as the volume of the droplet is fixed, the minimization of the droplet surface energy under the constants of a fixed droplet volume, it is as good as minimizing the surface area. And for a given volume, the surface area for a sphere is the least. Therefore the liquid droplet or bubble, it attains a spherical shape on account of surface tension in order to be in equilibrium by minimizing its surface energy. So always there will be a formation of spherical droplets because they are trying to attain the stable configuration, and that stable configuration is possible only by minimizing its net surface energy. And if keeping the volume fixed, the only way to minimize the surface energy is by reducing the surface area. And for a fixed volume, we know that the sphere has the least surface area, so it will always try to form a spherical shape. Also associated with this, we have one more effect, which is the wetting and the non-wetting of surfaces. Or some liquids like water tends to wet the surface, but some other fluids or liquids like mercury does not wet the surface. So let us see. Suppose we have a liquid droplet like this formed on a solid surface. So here we have three phases. This is the liquid phase, This is the solid phase and this is the gaseous phase. Let us say that the surface tension occurs for all these phases, and we will denote it different coefficient of surface tension. Let us say that the surface coefficient of surface tension between the gas and the liquid phase, which will be like this. Let us say that this is sigma Lg. Again we have sigma Ls between the liquid and the solid surface, and third we have sigma Sg. Now let us say that this angle, the contact angle, is theta. Now for equilibrium for this of this liquid droplet, let us try to do the force balance. Now this Lg can be resolved into its two components along the y-axis and the x-axis. So we have the two components of Lg as first will be sigma Lg cos theta, and the second will be sigma Lg sin theta. However, the vertical component, this will be balanced by the reaction force that will be acting on the solid surface. So, doing the force balance for both the x-axis and the y-axis, we have along the y-axis it is already balanced, but along the x-axis let us see what we have. Summation of forces in the x-axis, it must be equal to 0. So, we have sigma Sg. Then in the negative direction we have minus sigma Ls, and the y component of sigma Lg, which is sigma Lg cos theta. So we have minus of sigma Lg cos theta. This must be equal to 0, or we can say that sigma Sg minus sigma Ls, this is equal to sigma Lg cos theta, or this cos theta can be calculated as sigma Sg minus sigma Ls upon sigma Lg. Now this is an equation which is rather known as Young's law. And it tells us the various conditions when a liquid is wetting the surface or it is non-wetting the surface. So this Young's law have further implications. If the value of theta lies between 0 degree and 90 degree, then the liquid is termed as partially wetting, or equivalently the solid will be known as hydrophilic. So if the value of theta is greater than equal to 0 degree and less than equal to 90 degree, the the liquid is termed as partially wetting, and the solid substrate, it will be known as hydrophilic, which means an affinity towards water. Also, if theta is greater than 90 degree, then the liquid is termed as non-wetting and the substrate will be known as hydrophobic. So, if theta is greater than 90 degree, then the liquid will be non-wetting and the solid substrate, this will be known as hydrophobic. So these are the two implications, and we also have one special case when theta is equal to 0 degree. In that case, this represents a theoretically complete wetting. Now, these are the implications of Young's law, and this is also attributed to the energy minimization principle, because the liquid droplets, when over a surface, it will try to bring itself in a state of equilibrium, which it does by forming a spherical shape. And in that condition, we have, if we consider the three distinctive phases here, we can get the Young's law, which accounts for the wetting and non-wetting of the fluids.